The word equilibrium isn't new to us. Back when we learned Newton's laws, we found that if the net force acting on an object is equal to 0, that object won't accelerate. If it's at rest, it'll stay at rest. If it's in motion, it'll stay in motion. We're going to add to that today. And we're going to also say that if the net torque acting on an object is 0, that object will not accelerate in a rotational way. If you combine these two together, you have the truest state of equilibrium in which an object is neither accelerating linearly or rotationally. And that's what we call static equilibrium. Now take, for instance, a teeter-totter. If I have a weight acting on my teeter-totter, I'll call this M1G, at a distance of what I'm going to call R1, and I have a smaller weight, which I will call M2G, acting at a distance R2, we know from the labs that we've performed that these can be in equilibrium. We could set up this situation so that it doesn't rotate. But if we look at the other forces that are acting on this, we have to also consider the fact that this fulcrum that is supporting it in the middle is also exerting a force on this, and I'm just going to label this F. If I look at this in terms of vertical forces, I think it makes sense that the net force here would be F minus M1G minus M2G. This teeter-totter is not accelerating, so that means the net force must be equal to 0, and the acceleration is equal to 0. But also, the new thing that we've done recently is we've looked at this in terms of rotation. And I can say that the torque that is clockwise in this situation is the weight that causes the clockwise rotation times the lever arm, which in this case is just R2 because we have a perpendicular force here. The counterclockwise torque is being produced by the weight of mass 1, something like this. Now this is also equal to 0 because it's in balance and it's not rotating. Taken together, we have two equations that we can use to solve for two unknowns if we had that situation. We can look at many other situations in terms of not only the linear equilibrium, but the rotational equilibrium. Another example might be a situation where you have, let's say, a board that's being supported in two different places. Now, one of the things I'm going to have to draw into this situation that's different than before is the center of mass of this board. I put a little CM for that. The center of mass is important because the center of mass is where I can consider all the weight of that board to be located. We know that the mass of this board is distributed along the entire length of the board, but for purposes of doing calculating torques and equilibrium, I can say that all the weight of this entire board, which I'm going to call MB, mass of the board, times G, is located. I'm just going to call the force that supports it on this end F1, and the support force over here F2. Now this board has an overall length. If I just look at this in terms of the vertical forces, we're going to come up with a really similar equation to the first example we looked at. The up forces minus the down force equals 0. Let's say in this problem, we know the length of the board, and we know how far each of these forces is from the center. If I'd like to know what those two support forces are, this equation is not enough. It's got two unknowns in it. But let's look at this in terms of torque. The net torque acting on this board is 0. Pretty obvious, it's not rotating. So we have to set up an equation that expresses the balance in those torques so we can have a second equation to solve for our second unknown. This is where it gets tricky because torques are always referenced from the axis of rotation. I'm not looking at an object that has an obvious point of rotation. Not like my teeter-totter. This is a very obvious point of rotation for my teeter-totter. And the reason I didn't consider this force in my torque equation is because the distance from this force to the center or the axis of rotation is 0, so it just doesn't enter into the picture. But going back to what I'm looking at here, there really isn't an obvious place that this thing would rotate by. So I get to pick one. The spot you pick for the axis of rotation is totally irrelevant. So I'm just going to pick this place right here. I'm going to put a little X there and write CM. No, I'm not. I'm going to put an X here and note that that is my axis. And again, I could put it anywhere else. I could put it at the center of mass, I could put it over here, I could put it at the end of the board, but I'm choosing that spot. Now what I'm going to do, thinking of this as the place of rotation, the axis of rotation, I can look at this force here and say, that looks like it would produce clockwise rotation on this object. And I can look at this force over here and say, that looks like it would produce counterclockwise rotation on this object. So now I'm going to write an expression for the torques. Torque being force times distance, the force is the weight of the board, and the distance from the axis of rotation is R1, this distance here. The counterclockwise, I've got force 2, which is acting a distance of R1 plus R2. And what's it all equal to? 0, because those are my two torques, and the net torque here is adding up to 0. Now I think what you can see, if I know the two R's, and I know the mass of the board, the only thing I don't know in this equation is F2. I can solve this equation for F2, plug that into this equation, and then solve for F1. Now I don't want you to write down these formulas. These problems can be stated in any number of ways. We could, instead of giving you the R1 and R2 here, I could give you the length of this board and tell you the distance from this end. I could do any number of things to describe where those forces are acting, and that's why you never ever want to write down canned formulas for this type of problem. You have to draw a picture and build them from scratch.